Welcome back to the deep dive. Now, if you're an AMT student, you've probably spent a lot of time deep in the aircraft structure, right? Pneumatics,
For
engines.
real nuts and bolts stuff.
Exactly. But now we're hitting a really critical pivot point in modern aviation. We're talking electronics.
Yeah, this is where we shift from the sheer mechanical strength to the, let's call it the intelligence of the aircraft.
The systems that make today's complex, high-traffic flight possible. And crucially, safe.
Absolutely. I mean, think about it. You're moving from the wrench, maybe, to the oscilloscope.
Yeah.
This is communications and navigation, essentially the aircraft's operational brain.
And the airspace today?
Okay.
It's incredibly crowded.
Thousands of aircraft up there at any one time.
Yeah.
Without these electronic systems working perfectly, reliably, you'd have gridlock or worse, serious safety risks.
Okay, so let's frame this. We're diving into the world of avionics. That word itself is a bit of a blend, isn't it?
It is. Aviation plus electronics.
Yeah.
It didn't really become common until the 1970s or so.
And for you, the AMT student listening, understanding your specific role here is just paramount. It's a bit different from fixing a hydraulic leak.
It really is. You're dealing with modern solid-state units. Very reliable stuff, usually. Now, the actual repair of what's inside that box, the tiny semiconductors, that's often reserved for the manufacturer or specialized FAA-certified repair stations. It needs, micro-soldering, super clean environments, specialized test gear.
Right. But that definitely doesn't let the flight line AMT off the hook.
Oh, not at all. Far from it. Your responsibility is huge. It's non-negotiable, really.
Which is?
You're responsible for the installation, the inspection, the day-to-day operational maintenance, and crucially, ensuring the proper functionality of everything connecting that box to the aircraft.
So not the microchip itself, but everything around it.
Exactly. The antennas, the wiring bundles, all the connectors, the cooling systems, the vibration mounts, the performance of that whole expensive system, it relies 100% on your work.
Makes sense.
Yeah.
If you install a fancy antenna badly.
Then that, $200,000 navigation box might as well be a paperweight. It just won't work right.
Okay, to really get why these avionics systems are so dominant now, kind of have to look back at how fast they evolved. It was breakneck speed, really.
It was. And like a lot of aerospace leaps, the initial push, the urgency, often came from conflict.
Wartime needs.
Yep. We see the very first sort of basic ground-to-air voice communication tests happening way back. Think 1917, during World War I.
But that was just the spark, right? What really drove the navigation side?
That was civil aviation. The need to make money, basically. In the 1920s, commercial flight was taking off, but they had a huge problem: blind flight.
Flying without seeing the ground. In clouds or fog.
Precisely. If you got caught in the soup, you were lost. No visual references. So there was this huge push to develop electronic radio beacons, some way to find your direction.
And that tech progressed super fast.
Incredibly fast. I mean, going from just knowing the rough direction of a beacon to actually landing an aircraft entirely using radio signal.
Wow, when was that?
By the 1930s, they actually pulled off the first all-radio-controlled blind landing. It proved that even those early, relatively primitive electronic aids could guide a plane with surprising precision.
Then came the 1940s. WWAI.
Right. And that just injected maximum urgency. Development went into overdrive, pushing radio tech into the very high frequencies VHF.
And that wartime investment paid off afterwards.
Directly. It led straight to the foundation of the U.S. navigation system we still partially use today, the VOR network. The very high-frequency omnidirectional range, that was established by the late 1940s.
But the real game changer, the thing that defines basically every piece of avionics we touch today, that also came out of the 40s, didn't it?
Absolutely. The invention of the transistor, that was pivotal.
Before that, it was all vacuum tubes.
All tubes, which were massive, needed tons of power, generated lots of heat, and were incredibly fragile. Glass tubes don't like vibration.
Not ideal for an airplane.
Not at all. So when transistors were refined in the 1960s, giving us small, rugged, reliable solid-state radios and nav gear, that was the revolution.
And that's where the maintenance picture really changes for the AMT student.
Right, because these modern solid-state digital boxes, they have a very high mean time between failures, MTBF.
Meaning they just don't break very often.
Exactly. Compared to the old mechanical gyros or tube radios, their maintenance rates are way, way lower.
So you're less likely to be troubleshooting a bad component inside the box itself.
Much less likely. You're far more likely to be tracing why the system isn't getting a good signal. And that usually points back to things like a corroded connector, maybe a bad antenna installation, or some damaged coax cable, the stuff you install and maintain.
That reliability must have changed the economics of aircraft, too.
Oh, dramatically. When avionics first really took off, especially complex military systems, they were incredibly expensive, custom-built stuff.
I read somewhere that for some military planes, avionics could be up to, what was it, 80% of the total cost?
It's a staggering figure, right? 80%.
Yeah.
But mostly due to things like targeting pods, complex sensor suites, electronic warfare gear.
But that trend is reversing now.
It is, thankfully. Thanks to huge advances in digital electronics, microprocessors, and just global manufacturing scale, the cost ratio for sophisticated systems is actually starting to decline.
So things like digital glass flight decks.
Exactly. Used to be only on the biggest airliners. Now they're common in brand new general aviation planes, and they're hugely popular as retrofits for older aircraft. That's a big service area for maintenance shops.
And looking just ahead, the whole structure of the airspace itself is changing right now under this banner of Next Gen.
Yeah, Next Gen is the FAA's massive overhaul program for the entire national airspace system. It's scheduled to run through 2025.
What was the driver? Just too much traffic.
Pretty much. The FAA's traffic projections showed the system heading for gridlock. Just couldn't handle the volume safely or efficiently.
So what's the core technology shift here? It's not just better ground radar, is it?
No, the big pivot is towards satellite-based technology, specifically using GPS, global satellite positioning, fused with something called ADS-B.
ADS-B.
Automatic Dependent Surveillance Broadcast. Instead of ground radar finding the plane uses GPS to know its own precise position, and that it broadcasts that position, along with other data like altitude and speed, to air traffic control and even to other nearby aircraft.
So the aircraft are telling ATC where they are directly.
Exactly. It's automatic because it does it without pilot input. Dependent because it depends on the aircraft's own navigation system, usually GPS and surveillance broadcast, because it broadcasts the surveillance data out.
And this confirms that for the AMT, the focus has to stay locked on digital electronics.
Absolutely. ADS-B provides much more precise real-time position data than traditional radar. This allows for tighter spacing between aircraft, which massively increases system capacity and efficiency.
And it's mandatory now in many places.
Yep. Installation and proper maintenance of certified GPS receivers and ADS-B out transponders are required to fly in most controlled airspace in the U.S. and many other parts of the world. It really solidifies the AMT's role as the guardian of that digital cockpit.
Okay, we need to lay some groundwork here. How these systems actually handle information. It starts with a fundamental split. Analog versus digital.
Right. Think of analog as continuous and proportional, like an old mercury thermometer. The mercury rises smoothly, continuously, in proportion to the temperature.
So in electronics, the voltage changes smoothly.
Exactly. The voltage is continuously altered by whatever the input is. Like sound waves hitting a microphone create a continuously varying voltage. On an oscilloscope, you'd see a smooth, flowing curve.
And digital is the opposite, not smooth.
Correct. Digital is discontinuous. It takes that smooth, real-world input and chops it up. It captures it as discrete, separate samples of specific values.
Represented by on or off F states.
Precisely. Electronically, it's all about successive chains of voltage presence, that's logic 1, or OMN, and voltage absence, logic 0, or OF, just those two states.
Now, why is digital so dominant in avionics? What's the big advantage?
The huge advantage, especially where safety and integrity are paramount, is its noise immunity.
Noise. Like static.
Yeah, exactly. Analog signals are really vulnerable to noise. Unwanted static, background electrical interference, slight imperfections in the circuit. Anything like that can alter that smooth voltage curve.
And the system can't tell the difference between the real signal and the noise.
Right. But digital, it's highly immune. The system doesn't care about tiny fluctuations in voltage. It only cares if the voltage is clearly above a certain threshold that's a 1 or clearly below another threshold that's a 0.
The small variations get ignored.
They just get ignored. It's either on or O off F. There's no ambiguity. This rock-solid stability, this reliability, is why digital is absolutely essential for things like flight controls, navigation, anything safety critical.
Okay, so let's talk components, the things that actually manage these electrons. We should probably give a nod to the ancestors, the vacuum tubes, even though you won't fix them much.
Yeah, it's worth mentioning them just to see how far we've come. Tubes were the first electronic control valves. The simplest was the diode, just two elements, let current flow one way.
Like a check valve.
Exactly. Then came the triode, adding a third element, the grid. That was huge because a small voltage on the grid could control a large flow of electrons between the other two elements. That was the first electronic amplifier.
And there were more complex tubes, tetrodes, pentodes.
There were, adding more grids for better high-frequency performance or power handling. But honestly, for the AMT student, the deep functional details aren't the point.
What is the point then?
The key takeaway is simple. Tubes were big, they needed lots of power, usually high voltage, they got really hot. And crucially, they were made of glass, highly susceptible to shock and vibration, everything you don't want in an aircraft.
A maintenance nightmare waiting to happen.
Pretty much, which is why the transistor, being small, rugged, low power, was embraced so quickly. Much higher MTBF.
Okay, that brings us squarely into the modern world. Solid-state devices and semiconductors. Now, we don't need a deep dive into quantum physics.
No, definitely not. Let's skip the atomic valence shells for now. Focus on the practical function. We're talking mainly about silicon, which is naturally sort of an insulator, but we manipulate it chemically through a process called doping.
We're intentionally adding impurities.
That's exactly right. We create two types of silicon. One type, N-type, is doped with elements that have extra electrons, so it has free electrons floating around, ready to carry current. And for negative charge carriers,
And the other type.
that's P-type. It's doped with elements that have fewer electrons than silicon. This creates absences, electrons, which we call holes. These holes act like positive charge carriers, P for positive.
And the magic happens when you join them together.
Precisely. When you join a piece of P-type and a piece of N-type material, you create the fundamental building block, the PN junction. This forms a diode.
And that junction acts like a one-way street.
It does. If you apply voltage in the right direction, we call it forward bias. Connecting the negative battery terminal to the N-type and the positive to the P-type current flows easily. Once you overcome a small voltage barrier, maybe 0.7 volts for silicon,
But if you reverse the voltage,
apply it the other way. Reverse bias, the junction effectively widens, and it blocks the current flow, almost completely, except for maybe a tiny leakage current.
and sometimes we actually want to operate in that reverse bias state,
Yeah.
like with Zener diodes.
Exactly. A Zener diode is specifically designed to handle a controlled breakdown in reverse bias at a very specific voltage, the avalanche voltage. This makes them perfect voltage regulators. They clamp the voltage at that specific level, protecting sensitive circuits downstream, crucial in aircraft power systems.
Okay, so manipulating this PN junction, that ultimately leads us to the absolute foundation of the digital age, right? The transistor.
That's the one. Think of a transistor as a semiconductor sandwich, usually NPN or PNP, 3 layers. Emitter, collector, and a very thin layer in the middle called the base.
And the base is the key.
The base is the control handle. Here's the principle, and it's central to everything in avionics. A very small voltage or current applied to the base controls a potentially much larger current flow between the collector and the emitter.
So, tiny signal in controls big current out.
You got it. It can act as an amplifier, boosting the signal, or, more fundamentally for digital logic, it acts as a switch.
Base so in, current flows between collector and emitter. Base, off 3F, current stops.
Bingo. An incredibly fast, reliable, solid-state electronic switch. With no moving parts, low power, very rugged. And that simple switching capability is the basis for all digital logic, from the simplest gate circuits to the billions of transistors making decisions inside a modern microprocessor.
Okay, building on that switch idea, there are a few other specialized components we should touch on, especially for power control, like the SCR.
Right, the silicon-controlled rectifier. Think of it as a diode with an extra terminal, the gate. It normally blocks current in both directions, but if you give a small positive pulse to the gate while forward voltage is applied, it snaps on around and conducts current like a regular diode.
And it stays latched on.
It stays latched on even after the gate pulse is gone until the main current drops to 0, which happens naturally in an AC circuit. This makes SCRs great for controlling AC power, like in light dimmers or motor speed controls, by deciding when in the AC cycle to turn them on.
But SCRs only conduct in one direction, right? So they only control half the AC cycle.
Correct. If you need to control the full AC cycle, maybe for high-power heating elements like anti-ice systems, you need something else.
Which would be?
A triac. Functionally, a triac is like two SCRs connected back-to-back with a shared gate. It can be triggered to conduct current in either direction by a pulse on the gate. This gives you full control over the entire AC waveform, which is essential for efficiently managing high-power AC loads.
Okay. And finally, the real workhorses inside those glass cockpit displays and flight computers, MOSFETs and CMOs.
Yeah, these are crucial. If the basic transistor, often called a bipolar junction transistor or BJT, is the fundamental switch, the MOSFET metal oxide semiconductor field effect transistor is an evolution designed for high density and low power.
What's different about it?
The key is the metal oxide semiconductor part. There's an insulating layer, usually silicon dioxide, separating the gate terminal from the main current channel. This means practically zero current flows into the gate to control it.
Advantages.
Very high input impedance, which means it doesn't load down the circuit driving it, and very low noise.
Right.
Essential characteristics when you're trying to pack millions or even billions of these switches onto a single tiny chip.
Like CMOS builds on that.
Right. CMOS stands for complementary MOSFET. It uses pairs of MOSFETs, one N channel and one P channel, wired together in a complementary way. The beauty of CMOS is that in a steady state, either logic 0 or logic 1, one of the transistors in the pair is always OFF, meaning the circuit draws almost no power except when it's actively switching states.
Super efficient.
Incredibly efficient. This low power consumption and high density is why CMOS technology is the absolute foundation of virtually all modern integrated circuits, the ICs, the microchips in your aircraft's avionics suite today. Everything from engine monitoring to flight management systems relies on CMOS logic.
Okay, even though the world is going digital, we still need some basic analog circuits, right? Especially for power. The aircraft's generator or alternator usually makes AC power first.
That's right. And we need DC power for most electronics. So first step is rectification, changing that AC to DC.
Simple rectification isn't very efficient, is it?
No, using just one or two diodes wastes at least half the power. The standard is the 4-diode full-wave bridge rectifier. That uses the entire AC cycle, both positive and negative halves, making it much more efficient.
But aircraft often use alternators that produce three-phase AC. That needs a different setup.
It does, and it's actually even better. Aircraft alternators typically generate 3 separate AC outputs, phase shifted by 120 degrees from each other.
And we'll use a 6-diode rectifier for that.
Exactly, a 6-diode, 3-phase AC rectifier. The beauty is, because the AC phases overlap, the output DC voltage is naturally much smoother than even a single-phase bridge rectifier. The voltage never drops all the way to 0 before the next phase picks it up.
Which means cleaner, more stable DC power for the aircraft bus.
Precisely, which is critical for keeping those sensitive avionics happy.
Okay, power conditioned. What about handling signals? We need amplifiers to boost weak radio signals or maybe drive actuators. You mentioned 3 basic transistor configurations earlier.
Correct. Based on which of the 3 terminals, emitter, base, or collector, is common to both the input and output circuits.
First up, common emitter.
That's your workhorse voltage and power amplifier. It gives you good voltage gain and good current gain, so high power gain overall. The key thing for a technician to remember, though, is that it inverts the phase of the signal.
Output is 180 degrees out of phase with the input.
Exactly. If a positive going signal goes in, a negative going signal comes out.
Okay, then common collector, sometimes called an emitter follower.
Right. This one's different. It gives you high current gain, but almost no voltage gain. The voltage gain is close to 1. Its main job is impedance matching.
Impedance matching.
Yeah, it takes a high impedance input signal and provides a low impedance output signal without inverting the phase. Output follows the input. This is great for driving low impedance loads like speakers or long cables without losing signal strength.
Makes sense. And the third one, common base.
Common base gives you high voltage gain, like common emitter, but it has low current gain, actually slightly less than 1. Its input impedance is very low, and its output impedance is high.
Where would you use that?
It's often used in radio frequency RF circuits, especially at higher frequencies, partly because of that low input impedance. And like the common collector, the output signal is in phase with the input.
Now you're amplifying an AC signal like a radio wave. Why is DC biasing voltage so important for the technician to check?
That's crucial. Remember, an AC signal swings both positive and negative relative to 0. A transistor needs a certain small forward voltage just to turn on and start conducting.
Right, that 0.7 volts for silicon.
Exactly. If you just fed the raw AC signal to the base, the transistor would turn completely O off F during the negative half cycle. That would distort the signal badly.
So the DC bias keeps it turned on.
Precisely.
Okay.
You apply a steady DC voltage, the bias, to the base, enough to keep the transistor conducting nicely right in the middle of its active region. Then, the AC signal rides on top of that DC bias, swinging the transistor's conduction up and down, but never shutting it off completely. This ensures clean, undistorted amplification of the entire AC waveform. Checking that bias voltage is a key maintenance step.
Okay, so we can condition power, we can amplify signals. But how do we create the specific frequencies needed for radio communication in the first place? That's oscillators, right?
That's the job of the oscillator.
Yeah.
Converting DC power into an AC waveform, like a sine wave, square wave, or sawtooth wave at a specific desired frequency.
How do they work? I remember something about a tank circuit.
Yeah, the basic concept often involves a tank circuit, which is just a capacitor and an inductor, a coil, connected in parallel. If you charge the capacitor and then connect it to the coil, energy starts sloshing back and forth between them.
Like water in a tank?
Kind of. The capacitor discharges through the coil, building up a magnetic field. Then the field collapses, inducing a current that recharges the capacitor, but with the opposite polarity. This back and forth creates an electrical oscillation, a sine wave.
But wouldn't that oscillation just die out because of resistance in the wires?
It would. It creates a damped oscillation that fades away quickly. That's why practical oscillators need an active component, usually a transistor, to sustain the oscillation.
Like the Hartley oscillator.
The Hartley is a classic example. It uses a transistor amplifier with a tapped coil in the tank circuit. A portion of the oscillating signal is fed back to the transistor's input in the correct phase to overcome the losses due to resistance.
So the transistor acts like you're pushing a swing at just the right moment.
That's a great analogy. It keeps adding just enough energy back into the tank circuit in each cycle to replace what's lost, resulting in a continuous, stable AC output at the circuit's resonant frequency.
But for air traffic control, that frequency needs to be incredibly precise and stable, right? Not drifting around.
Absolutely. You can't have your comm radio drifting off frequency. That's where crystal control comes in.
Using quartz crystals.
Exactly. Certain materials, especially quartz crystals, exhibit the piezoelectric effect. If you apply a voltage, they physically deform slightly. Conversely, if you physically stress or vibrate them, they generate a voltage.
And they vibrate at a very specific frequency.
Extremely specific and incredibly stable, determined by how the crystal is cut. So you incorporate this quartz crystal into the oscillator circuit, usually in the feedback path. The crystal will only allow feedback at its precise resonant frequency, effectively locking the oscillator to that frequency with very high accuracy and stability. Almost all aviation transmitters use crystal-controlled oscillators for this reason.
Okay, we've generated our precise frequency. Now, how does that radio signal actually get from the transmitter to the receiver? We need to understand radio propagation and the spectrum.
Right. Radio waves are electromagnetic energy, just like light, but at lower frequencies. They travel at the speed of light, about 186,000 miles per second. The key relationship to remember is that frequency and wavelength are inversely proportional.
High frequency equals short wavelength.
Yep. And low frequency equals long wavelength. And how these waves travel, how they interact with the Earth and the atmosphere, depends heavily on their frequency. This determines which frequency bands we use for different jobs.
Okay, let's start with the lowest frequencies, longest waves.
Those are ground waves. These are typically in the very low frequency, VLF, low frequency, LF, and medium frequency, MF bands, say, from 3 kilohertz up to maybe 3 millihertz. Because of their long wavelengths, they tend to follow the curvature of the Earth.
So they can travel long distances beyond the horizon.
They can, which is why these frequencies were used for early long-range navigation systems like LORAN, now defunct, and are still used for ADF, automatic direction finder beacons.
Okay, moving up in frequency.
Next, you get skywaves, typically in the high-frequency HF band, maybe 2 to 25 or 30 megahertz. These waves travel in straight lines, but they have the interesting property of reflecting, or more accurately, refracting, off the ionosphere.
The ionosphere, that layer high up in the atmosphere.
Right. It's a layer of ionized gas particles. HF radio waves hitting it can be bent back down towards Earth, so the signal can bounce between the Earth and the ionosphere multiple times.
Allowing communication over huge distances.
Exactly. Well beyond the horizon. This is why HF radio is still essential for long-distance communication, like transoceanic flights where you're out of range of VHF stations. The downside is that the ionosphere's condition changes with time of day and solar activity, so HF propagation can be unreliable sometimes.
Okay, and finally, the frequencies most pilots and technicians deal with daily.
That would be space waves. These are in the very high frequency, VHF, ultra high frequency, UHF, and super high frequency, SHF, bands and above. These frequencies travel strictly in straight lines, line of sight.
They don't follow the Earth's curve, don't bounce off the ionosphere?
Nope, they just go straight out into space, or until they hit something. This means the transmitting and receiving antennas must be able to see each other, electronically speaking. Any obstruction, like a mountain or the curvature of the Earth itself, will block the signal.
And this is where most modern aviation comms and nav aids operate.
The vast majority. Standard VHF voice communications, typically 118.0 to 136.975 MHz, are space waves. VOR and ILS localizer are VHF. Glide slope DME, transponders, GPS, satellite communications, those are all UHF or higher. Line of sight is the key limitation.
Got it. Now, we have the carrier wave at the right frequency, traveling the right way. How do we actually put information onto it? That's modulation.
Modulation is the process of encoding information onto that carrier wave. The most common type used for aviation voice comms is amplitude modulation, AM.
Changing the amplitude, the height or power of the wave.
Exactly. The information signal, your voice converted to electrical signals, varies the amplitude of the high-frequency carrier wave. The receiver then detects these amplitude variations and reproduces the original voice signal.
What's the downside of AM, especially for aviation?
The main drawback is its susceptibility to noise. Lightning strikes, electrical equipment, atmospheric static, they all create amplitude variations. An AM receiver has a hard time distinguishing between the noise and the intended signal variations. That's why AM radio can sound noisy or staticky.
Okay, so what's the alternative? I know FM radio sounds cleaner.
It does. Frequency modulation FM works differently. Instead of varying the amplitude, the information signal varies the frequency of the carrier wave slightly, while the amplitude stays constant.
And since most noise affects amplitude,
An FM receiver can largely ignore amplitude variations, making it much more immune to static and noise. This gives FM superior fidelity, much clearer sound. The trade-off is that FM typically requires a wider frequency bandwidth than AM.
and what about those long-distance HF comms? You mentioned efficiency being key. That leads to single sideband, SSB.
Right. When you amplitude modulate a carrier wave, you actually create three components. The original carrier wave frequency, an upper sideband carrier frequency plus audio frequencies, and a lower sideband carrier frequency minus audio frequencies.
And both sidebands contain the same information.
Exactly the same information, just mirrored. And the carrier itself contains no information but uses up most of the transmitter power. So SSB is a clever way to improve efficiency.
How does it work?
It filters out or suppresses the power-hungry carrier wave and one of the redundant sidebands. It only transmits a single sideband.
Having the bandwidth needed.
Roughly halves the bandwidth, yes. And since you're not wasting power transmitting the carrier and the other sideband, all the transmitter's power can be concentrated into that one information-carrying sideband. Much more efficient for power and spectrum use, which is critical for those challenging long-range HF paths.
Makes sense. Okay, last piece of this puzzle. Getting the signal from the radio into the air and vice versa. Antenna design in the ground plane. This is very hands-on for the AMT.
Absolutely. Antennas are critical. They need to be efficient radiators and receivers at the specific frequency they're designed for. Key characteristics are length, polarization, and directivity.
Length seems most fundamental. How is that determined?
Antenna performance peaks when its electrical length is resonant with the wavelength of the signal. The most common resonant length is a half wavelength. There's a basic formula every AMT student should know for calculating this. Antenna length in feet equal 468 divided by the frequency in megahertz.
So for a typical VHF comm frequency, say 120 megahertz, 468 divided by 120. That's about 3.9 feet for a half-wave antenna.
But a nearly 4-foot antenna isn't always practical, especially on smaller aircraft or for higher frequencies where it would be tiny.
So we use shorter antennas.
Often, yes. A very common design, especially for VHF comms, is the Marconi antenna, which is electrically a quarter wavelength long.
But you said resonance happens at a half wavelength. How does a quarter wave antenna work?
This is where the ground plane comes in. It's a crucial concept. The Marconi antenna uses the aircraft's conductive metal skin as the other half of the antenna system. The metal skin acts like an electrical mirror, effectively creating an image of the quarter wave vertical element below it.
So the physical quarter waves plus the electrical image equals the needed half wave.
Exactly. The antenna and its image in the ground plane resonate together as a half-wavelength system. This is why proper bonding of the antenna base to the aircraft structure is absolutely critical.
What if the aircraft skin isn't metal, like a fabric-covered plane or a composite structure?
Then the technician must create an artificial ground plane. This is a direct maintenance task. You might install metal foil, copper tape, or a specific pattern of wires onto the inside of the non-conductive skin, directly underneath where the antenna will be mounted.
And this needs to be electrically bonded to the main airframe structure.
Yes, it has to provide that conductive surface for the antenna to work against. An inadequate or improperly installed ground plane is a guarantee of poor radio performance, no matter how good the radio or antenna is.
Okay. We also see different shapes of antennas, like the V-shaped ones for VOR.
Right. That V-shaped antenna is a type of dipole antenna specifically designed to receive the horizontally polarized VOR signals effectively. Your typical VHF comm antenna is a vertical Marconi type, radiating and receiving vertically polarized signals omnidirectionally, equally well in all horizontal directions. And then you have loop antennas, which are highly directional, used in ADF systems to find the null point of a signal.
And connecting the radio to the antenna, we can't just use any wire.
Definitely not. You absolutely must use coaxial cable or coax. It has a center conductor surrounded by insulation and then a braided metal shield around that, all covered by an outer jacket.
Why is the shield so important?
2 reasons. It shields the center conductor from picking up external interference, and it prevents the signal on the center conductor from radiating out and potentially interfering with other systems on the aircraft. It keeps the signal contained.
And impedance matching is key here, too.
Critical. The impedance of the coax cable, typically 50 ohms for most aviation applications, must match the impedance of the radio's output and the antenna's input. If there's a mismatch, signal power gets reflected back from the connection points, reducing efficiency and potentially even damaging the transmitter over time. Ensuring good quality coax, proper connectors, and correct installation without sharp bends or damage is a huge part of the AMT's job for reliable ComNav performance. Poor coax or connectors are probably one of the most common culprits for intermittent radio problems.
All right, let's pivot now specifically to navigation systems, starting with the real cornerstone of the pre-GPS airway structure, VOR, VHF omnidirectional range.
Yeah, VOR was and still is foundational. There are thousands of VOR ground stations. Each one transmits 2 VHF signals.
2 signals.
Yep. One is a reference signal. Think of it as a non-directional signal that's the same in all directions, representing magnetic north, or 0 degrees, from the station. The second signal is a variable signal, whose phase changes as it electronically rotates 360 degrees around the station, like a lighthouse beam sweeping around.
And the aircraft receiver compares these 2 signals.
Exactly. It measures the phase difference. This is essentially the time difference between receiving the peak of the reference signal and the peak of the variable signal. That phase difference directly corresponds to the aircraft's magnetic bearing, or radial, from the VOR station.
So if the variable signal is 90 degrees out of phase with the reference, you're on the 090 radial from the station.
Precisely. On the flight deck, the pilot uses the omni-bearing selector, the OBS knob, to select a desired course, a radial TO, or from the station. The course deviation indicator, the CDI needle, then shows if the aircraft is left or right of that selected course.
And those dots on the CDI display.
Each dot typically represents 2 degrees of deviation. So if the needle is 2 dots to the right, you're 4 degrees left of course and need to turn right. The tow from flag tells the pilot whether the selected course will take them towards or away from the station, resolving that 180-degree ambiguity.
Okay, now from the maintenance side, VOR checks are a big deal, right? Especially for IFR flight.
Huge deal. These systems have to be periodically checked for accuracy. There are published procedures using certified ground checkpoints or airborne checks over known landmarks, or dedicated VOR test facilities, known as VOTs, often located right on an airport.
And the VOT check has a very specific procedure and tolerance.
It does. Using a VOT is often the easiest. You tune the VOR receiver to the specific VOT frequency, which is usually 108.0 MHz. Then you center the CDI needle using the OBS knob.
And what should the OBS read?
When the needle is centered, the OBS should read either DRL circ with a from indication or 180 circ with a TO indication. That's the baseline.
And the critical number, the tolerance the AMT absolutely must know and verify.
This is a number to memorize. For the aircraft to be legal for IFR flight using that VOR receiver, the difference between the OBS reading, when centered on the VOT signal, and the expected 0 from or 180 TO reading cannot exceed plus or minus 4 degrees.
4 degrees max error.
Max. If the check shows a 5-degree error, that system is NO-GO for IFR until it's repaired and rechecked. Documenting this check properly in the aircraft logs is a critical maintenance task.
Got it. Okay, let's step back in time a bit to the older low-frequency systems. ADF, automatic direction finder, and the ground stations they use, NDBs, non-directional beacon.
ADF is simpler in principle. It operates down in the LF and MF bands, 190 kilohertz up to around 535 kilohertz, sometimes even tuning commercial AM radio stations for navigation. It basically just points a needle towards the NDB station.
Older versions were tricky, though. Something that ambiguity.
Yeah, the earliest radio direction finders, RDF, use a simple loop antenna which has a null, a point of minimum signal when its edge points towards the station, but also when its edge points 180 degrees away. The pilot had to maneuver to figure out which null was the correct one.
Not ideal. How did ADF solve that?
Modern ADF systems use a combination of antennas. They still have a directional loop antenna, often electronically rotated now, not physically, to find the sharp nulls, but they combine its signal with a non-directional sense antenna.
And combining the signals resolves the ambiguity.
It does. Processing the signals from both the loop and sense antennas together electronically creates a reception pattern with only a single clear null, or more commonly, a single peak, ensuring the ADF needle always points directly to the station, not away from it.
What's the key maintenance check for an ADF system? You mentioned installation earlier being critical.
It's all about alignment. Because the system relies on the physical or electronic orientation of that loop antenna relative to the aircraft's nose, its calibration is absolutely critical. The technician must perform precise alignment procedures, often called swinging the ADF, to ensure the needle indication accurately reflects the magnetic bearing to the station relative to the aircraft's longitudinal axis. Any error in installation or calibration means the navigation guidance is wrong.
Okay, and one more thing on ADF, the BFO switch. Beat frequency oscillator. Why does the pilot need that sometimes?
Good question. NDBs identify themselves by transmitting their call sign in Morse code. Most NDBs modulate their carrier wave with an audio tone for this. You hear dit-da-dee, etc. But some older or simpler NDBs transmit just an unmodulated carrier wave, signal type N0N A1A.
So you wouldn't hear the Morse code?
Exactly. The BFO circuit inside the ADF receiver generates an internal audio frequency signal. When you turn the BFO on N, this internal signal mixes, or beats, with the incoming unmodulated carrier wave from the NDB. This mixing produces an audible tone at the difference frequency, allowing the pilot to hear the Morse code identifier and positively identify the station they're navigating by. Can't navigate if you don't know what station you're tuned to.
Right, positive ID is key.
Oh.
Okay, now for precision approaches down to the runway. The Instrument Landing System, ILS.
ILS is the standard for precision approaches worldwide, providing both lateral left-right and vertical up-down guidance to the runway threshold. It's really 3 systems working together.
First part, horizontal guidance.
That's the localizer. It's a VHF transmitter usually located off the far end of the runway. It operates in the VOR frequency range, 108 to 111.95 MHz, but only uses frequencies with an odd first decimal digit, like 109.1, 110.3, 111.75, and it transmits 2 signals. Yep. It transmits 2 overlapping patterns. One side, typically the left side as you approach, is modulated with a 90 Hz tone. The other side, the right, is modulated with a 150 Hz tone. Right down the middle, on the runway center line, the strength of the 90 Hz and 150 Hz signals is equal.
And the aircraft's Vorl's receiver detects this difference.
Correct. The receiver, tuned to the ILS frequency, displays the difference on the same CDI needle used for VOR. If you're left of center line, the 90 Hz signal is stronger, needle deflects right, fly right. If you're right of center line, 150 Hz is stronger, needle deflects left, fly left. On center line, the needle centers.
Okay, that's left and right. What about up and down guidance?
That comes from the glide slope. This is a separate transmitter, usually located off to the side of the runway near the touchdown zone. It operates on UHF frequencies, which are automatically paired with the VHF localizer frequency when the pilot tunes the ILS.
So the pilot only tunes one frequency?
Correct. The glide slope works on the same principle as the localizer, but sideways. It transmits 2 patterns, One above the desired descent path modulated at 150 Hz, and one below the path modulated at 90 Hz.
Displayed on a separate indicator.
Usually, yes.
Got
A dedicated horizontal needle, the glide slope indicator. If you're below the ideal path, typically around 3 degrees, the 90 Hz signal is stronger, needle deflects up, fly up. If you're above the path, 150 Hz is stronger, needle deflects down, fly down. Stay on the 3-degree path, the needle centers. As a technician, you're often checking the glide slope antenna, usually near the nose, as it can get damaged.
Okay, localizer for left-right, glide slope for up-down. What's the third part of ILS?
Distance information provided by marker beacons. These are low-power, vertically aimed transmitters operating on a single frequency, 75 MHz. They're placed at specific points along the final approach path.
And they give audio tones and lights in the cockpit.
Exactly. As the aircraft flies over them, the 75 MHz receiver picks up the signal and activates a corresponding light and audio tone.
What are the markers?
The outer marker, OM, is usually located 4 to 7 miles from the runway threshold, often where you intercept the glide slope. It transmits a 400 Hz tone keyed with continuous dashes, and illuminates a blue light. The middle marker, MM, is typically about 3,500 feet from the runway threshold. It transmits a higher-pitched 1,300 Hz tone keyed with alternating dots and dashes, and illuminates an amber light. The inner marker, IM, if installed, usually only on C-3 precision runways, is very close to the threshold, marking the decision height point. It transmits a very high 3,000 Hz tone keyed with continuous dots and illuminates a white light.
Okay, those markers give distance points. But what about continuous distance information, especially when flying en route using VORs? That's DME, right? Distance measuring equipment.
Exactly. DME provides pretty precise distance information. It works in the UHF band, 962 to 1213 MHz. The aircraft's DME unit sends out paired pulses, an interrogation signal. A compatible ground station, usually a VOR-TAC, VOR plus military TAC-in, or a VOR DME, receives these pulses and, after a short fixed delay, transmits reply pulses back.
And the aircraft measures the time it takes.
Measures the round-trip time, subtracts the known fixed delay at the ground station, divides by 2, and converts that time into distance based on the speed of radio waves.
And it's automatically tuned with the VOR.
Usually, yes. When you select a VOR frequency that has DME capability, the associated DME channel is automatically selected too. So the pilot gets bearing from the VOR and distance from the DME, giving a very precise position fix, a range and bearing.
Now, there's a slight catch with DME distance, isn't there? Slant range versus ground range.
Yes. That's important for technicians and pilots to understand. Standard DME measures slant distance, the direct line-of-sight distance between the aircraft antenna and the ground station antenna.
So if you're flying high and close to the station,
the slant distance will be significantly greater than your actual horizontal distance over the ground. The extreme example is flying directly over the station at, say, 6,000 feet altitude, about 1 nautical mile. Your ground distance is 0, but the DME will read 1.0 nm because that's the slant distance to the station below you.
So you have to account for altitude, especially when close in.
You do. Although some more advanced digital DME systems, especially those integrated into flight management systems, FMS, can use the aircraft's altitude information to calculate and display the true horizontal ground distance, which is often more useful for navigation. But basic DME always reads slant range.
Okay, so VOR gives bearing, DME gives distance. Combining those allowed for the next step, didn't it? Area navigation, RNAV, flying point to point without needing to fly directly over stations.
Exactly. RNAV was a huge leap in flexibility and efficiency. It allows you to define navigation routes using geographical points, waypoints that don't necessarily correspond to the physical location of a ground-based navade.
How did the early pre-GPS RNAV systems work? They still use VOR DME, right?
They did. The early VOR-based RNAV systems used an onboard computer, often called a course line computer, CLC. The pilot would define a waypoint not as a physical station, but as a specific radial and DME distance from a nearby VOR DME station. For example, waypoint LFA is the 200-degree radial at 25 nautical miles from the XYZ VOR.
So you're creating a phantom station out in space.
That's a perfect way to put it, a phantom waypoint. The CLC would take the real-time bearing and distance information from the actual XYZ VOAME, do some trigonometry based on the defined waypoint's radial distance offset, and then calculate the aircraft's current bearing and distance to that phantom waypoint.
And it would display this information on the standard VOR instruments.
Yes, that was the clever part. It would manipulate the output signals going to the pilot's CDI and towframe indicator, making them behave as if they were navigating directly to or from that phantom waypoint. It basically tricked the existing instruments into providing guidance along the desired RNAV course.
Allowing much more direct routes between places.
Absolutely. Instead of zigzagging from VOR to VOR, you could fly straight lines between user-defined waypoints. These early CLC systems could be complex and required careful maintenance, but they really paved the way for the modern GPS-based RNAV and required navigation performance RMP operations that are standard in almost all cockpits today. Hashtag, tag, outro.
Wow. Okay, so we've covered a lot of ground in this deep dive. From the very first vacuum tubes and the invention of the transistor, all the way through radio waves, antennas, and up to modern satellite-driven navigation like GPS and ADS-B.
It's quite an evolution, and what's really clear is that today's aviation, both its high performance and its safety, is absolutely dependent on these digital electronic systems working flawlessly.
And for the AMT student listening, the takeaway really seems to be that your role has fundamentally expanded. You're not just a mechanic anymore.
Not at all. You have to be an avionics systems expert, too. You need that foundational understanding of the physics, how doping silicon creates a diode, how a transistor acts as that crucial switch, how radio wave propagation dictates antenna choice and placement.
Because that knowledge underpins every check you perform.
Absolutely. Whether it's verifying that critical PM4 SCRG VOR tolerance for IFR flight, ensuring the ADF antenna is perfectly aligned, or troubleshooting why a comm radio isn't transmitting clearly, it all comes back to understanding how these electronic systems are supposed to work.
Now, we talked about how the shift to solid state and digital meant higher reliability, right? Fewer actual component failures inside the box.
Generally, yes. MTBFs are much higher.
But as we move further into next gen, with glass cockpits integrating these incredibly dense computer chips containing literally billions of transistors, does that present a new, maybe different kind of maintenance challenge for the airframe technician?
That's a really interesting question to end on. I think it does. The challenge maybe shifts from focusing solely on internal component failure to focusing more on the external environmental factors affecting those dense electronics. Meaning, with that extreme component density packed into small spaces, things like system cooling become absolutely paramount. Microchips generate heat, and they fail very quickly if they overheat. So, ensuring cooling fans, airflow paths, and heat sinks are all functioning perfectly becomes a critical maintenance task.
And vibration.
Vibration, too. While the chips themselves are rugged, the sheer density of connections on the circuit boards, the solder joints, the connectors between boards, they can be vulnerable to fatigue from long-term vibration. So, ensuring proper vibration insulation through correctly installed shock mounts is more important than ever.
So the integrity of the installation itself is key.
Exactly. The overall installation integrity. Things like ensuring coaxial cables aren't chafing against structure, connectors are properly torqued and secured, moisture isn't getting into junction boxes. It's that meticulous attention to the system's environment, temperature, vibration, electrical noise, moisture protection that becomes the technician's primary role in ensuring the reliability of these incredibly complex, high-density digital systems. The focus expands beyond just the box itself.